started, again, I'd like to introduce our speaker. You weren't there last night, and I gave a little bit of background on Jerry, and I won't go into great details this afternoon, but it's a great pleasure to have Jeremy Trevika visit us. Corvallis fly out from Boston and talk to us this afternoon on postmodern geophysics and ice age climate.
Thanks, Peter. So I started yesterday's talk with the story, and I just told Peter I spent an hour in downtown Corvallis today. It's kind of small, intimate, and I sat next to a OSU, is it Beaver? Beaver doesn't create an image, does it, of a tight end for the football team. And I told him my story. I was telling some of the students at lunch. I was my high school football quarterback for 4 years. And I had a record that will never be beaten, ever. I lost 36 straight games. I was 0-36. And it tells you something about me, because even after the 34th or 35th loss, I walked into the dressing room and thought, you people stink. It never dawned on me I had any role to play in that. But the way my career ended is really the highlight of my sports career. I was gunning for a 0-40 perfect loss record, but I was fired 4 games from the end. And I was told to shower up and get going. And what happened was, as we were just a terrible football team, and as what normally happened, the ball was snapped to me. I was in fear for my life. The coach used to say that my wing talent was that I ran very quickly when I was scared. So the middle linebacker ran in, hit me in full run, threw me to the ground, and landed on top of me. Right? And the ball went who knows where, as it always did. And now I'm lying on the ground. You have to have this image from the sidelines. I'm lying on the ground with the middle linebacker on top of me. I'm there, and I recognize him. He was a friend of mine when I was in primary school, Mike Argyropoulos. So I'm lying there, and I say, Mike? And he said, Jerry. And I hugged him, which apparently you're not supposed to do in a football team. And I went to the sidelines, just happy that I'd met my old friend Mike, and the coach said, get dressed, you disgust me. And that was the end of my career, right? I left out that last part with the Beaver tight end today, though. Okay, so this is an allusion to I have several sisters who went through art history, so I stole this idea, postmodern geophysics and ice age climate. So it's for me a lot of fun, because it'll reach back a little bit into some of the work I did when I was a graduate student and update it with some recent work just published a few weeks ago. So I was trained in Toronto. Toronto is one of the great centers of plate tectonics. Tuzo Wilson was there. For those of you who know Tuzo, those who don't, you know, in Canada we'd call him the father of plate tectonics. Americans would use other names, I guess. But we were sort of steeped in the history of plate tectonics. And we were once asked, and I was at a workshop where people were asked, name the 3 most important papers in plate tectonics. And these were the 3 that I came up with. I guess I don't have a pointer, but that's okay. The first is Tuzo's paper. This is a famous paper that was the first to set out transform faults. The idea that all of these plate boundaries that we saw around the surface of the Earth were connected. They weren't isolated. They didn't come to ends. That's what he's saying there. The second was a paper by Dan McKenzie, who was a young graduate student at the time this paper was written, I think, with Jason Morgan. And actually, I have a continuation of this, because Jason, who was a professor at Princeton for many years, is retired now, but he's at Harvard. He has an office there, and I talk to him every day on the stability of triple junction. And the final one, the one that I particularly focused my career on early on, was this really famous paper by the Lamont group, Isaacs, Oliver, and Sykes, on a new global plate tectonics. And the reason this is important is that it was the first paper, in my view, in plate tectonics that really described the physics of it as a 3-dimensional process. It was no longer the 2-dimensional process we thought of. Even the terms continental drift, seafloor spreading, they connote a sort of horizontal motion. This was the first to show there was a 3-dimensionality to it. slabs, these places where plates were destroyed, involved the subduction of plates down into the mantle. And as a graduate student, although I was a graduate student well after this was really compelling to me because it was, I was a graduate student in mantle dynamics. I looked at mantle flow, and this was the first picture we had in some ways of mantle flow in action. And it seemed to me, as it did to many geophysicists in the 70s, 80s, some of them trained me as a graduate student, that this three-dimensionality was important, right? So if plate tectonics is the start of, or signals the modern era of geophysics, so what I'm going to talk to you about now is moving beyond plate tectonics and making connections, as I do, to paleoclimate in particular. And I'll give you a few examples where, without the sort of understanding that people like Lynn Sykes, who I met at Lamont when I met Sarah, right? He was there. I was shocked he came back after the talk and we had a long chat, where people like, all connections have been made to all sorts of fields in earth science, but my connection is to paleoclimate, of course, and I think I'll surprise you in showing you just how relevant an understanding of mantle dynamics is to paleoclimate research. So let's update this picture by Sykes, and we can take a look at sort of more recent work. This is important early study, in some sense, early, in this case in the 90s, studies by Peter Bungos now in Munich. He was one of the first to model mantle convective flow, thermal convection in the Earth's mantle that ultimately drives plate tectonics, and I'll show you also drives not only the sideways motion, but the up and down motion. He was one of the first to develop fully three-dimensional image of mantle flow. It's a hard problem. Well, actually not as hard as atmospheric dynamics. There's no inertia in the mantle. Things would stop dead if you stopped driving the system. These are important studies. I can't be at Harvard without showing a picture of seismic tomography. Adam Zawanski is at Harvard. He's one of the great pioneers of seismic tomography. Use seismic waves, travel times, body waves, even normal modes to image the Earth's interior, variations in seismic wave speed. This is an image, that's the Tonga Trench here, the New Hebrides, of a subducted slab underneath the Tonga Trench, which sits down on the 670-kilometer boundary that marks the boundary between the upper and lower mantle. And then eventually, because it just sat down there for tens of millions of years, fell through into something that used to be called mantle avalanches, now often referred to really awkwardly as slab-avalanches, right? These isolated, well, it used to be flushing events, but that wasn't any better, right? So periods in which slabs that rest on 670 sometimes fall through. And this has a lot of implications for the surface tectonics. You can time it such that this slab, knowing the viscosity of the Earth's mantle, this slab fell through 10 million years ago. And it marked the onset of the change in the tectonic system above there. New Hebrides had a slab that was directed southward. The polarity of slab changed. What was once a large subduction zone turned into two subduction zones connected by a transform fold. A total reorganization of the plate system because of this flushing event. And this is a paper that I wrote with a seismologist and with one of my former graduate students to explain the connection between mantle flow and that plate reorganization. So I'm going to be talking about mantle flow or mantle structure throughout this talk. I'll separate it into two parts. We'll look at ice age sea level, and just like yesterday I talked about rapid sea level change, today I'm going to start with a primer that will give you a 5-minute background course on what ice age sea level change is like. That is, the sea level change is driven by the late Pliocene glacial cycles. Then I'll look at two examples. All of these examples, in some sense, are taken, at least in part, from work of my graduate students, and I'll make note of that. One is, well, let me just leave it at saying I'll have two examples of ice age sea level. Then I'll talk about dynamic topography. So this is a field, in some ways, that I was on the ground floor of as a graduate student, wrote a series of papers. This idea that this motion, this mantle flow in the Earth's interior will push continents up and down, and led to a lot of enigmas being resolved in continental geology. But we'll talk about how that plate changes in continental elevation associated with mantle flow have really important implications for our understanding of ancient sea levels. But I have to define sea level first, because unlike last night's talk, here, if I don't define it carefully, you'll be confused. So, I just got several emails from geologists tend not to, I don't understand why they don't use these definitions, but They try to push for different definitions, but we're going to stick to these. Sea level is the difference in the height of the sea surface. I talk about a gravitational equipotential that defines the sea surface. That's very technical sounding. But the sea surface minus the sea bottom. You can define that globally. We talk about sea level over land all the time, right? But it is that difference, okay? And so a sea level change can happen either because the sea surface height goes up or down, or the land goes up and down. Either motions of either of those bounding surfaces lead to a sea level change. When you go to a shoreline, if you see an ancient shoreline that might be elevated 5 meters, you have no idea whether it was the water that dropped or whether the land came up, right? There's nothing in the geology that will tell the difference. The confusion has arisen in the literature because now, using satellites, we can tell how this sea surface changes independent of the sea bottom. And that's caused a lot of confusion in the literature. But I'll use the geological definition. It's this distance between those two surfaces. I'll also talk about eustasy. This is an often confused term. Eustasy is simply the globally average value of sea level change over the oceans. So you take the total integrated distance change between those two surfaces, you add it up. And that's a direct proxy for ice volume. Okay? The problem, and as you saw from my lecture last night, those of you who were there, is that some people take what is a definition that's convenient because it gives you a proxy for ice volume and assume that sea level works this way, that you actually have uniform changes in sea level. And that's not true, even remotely so, right? But we're going to avoid that. But I'll still use terms like eustasy just to define that globally average change. If you could go around the whole Earth's oceans and know how it has changed, take the average, that's the eustatic sea level change, okay? And that tells you something about ice volumes. Now, in postglacial sea level studies, up until very recently, the last few years, in fact, and certainly first careful analyses that departed from this were in 2009, 2010. This is very recent science. The assumption was that the Earth, in responding to changes in ice sheets and oceans, that Earth could be treated like an onion. Its structure varied with depth alone. There were no lateral variations in structure. The important variation was with depth. So for the elastic structure of the Earth, we use something that seismologists call PREM, the Preliminary Reference Earth Model. It's sort of a misnomer. It was written with the assumption that there'd be part 2, and that never came. So this is a 40-year-old seismic model that's still preliminary in a sense, but everybody uses. And in fact, uncertainties in parameters like the seismic wave speeds or the density within the Earth are 1% or less. The elastic structure of the Earth is very well known. Okay? Then we have to define viscosity. So viscosity is a material strength. Okay? And typically in Ice Age calculations, we discretize the Earth's, you don't see, there's barely a difference here. For some reason, it doesn't come through. But we have the core. When we talk about viscosity, we discretize in 3 layers. The lower mantle, that's below 670 kilometers depth, right to the core mantle boundary. The upper mantle, here, and the lithosphere. We'll define a viscosity in both those regions, and we'll just talk about having it overlain by an elastic plate. Because, of course, plate tectonics, plates are just pieces of the lithosphere, this top 100 kilometers or so. So we know all we need to know from seismology about the way the Earth's elastic structure varies internally. We don't know. There's lots of debates about what the viscosity, that is the strength of mantle material, is. So it's usually a free parameter that you vary in the modeling. Okay? But the important thing here is that nothing is varying laterally. And that kind of model has been used since the early 1970s. So 30 years, 40 years almost, of use of that kind of model. So now I'm going to show you numerical predictions of the way sea level changes because of the Ice Age, but you should have the understanding that underlying it is an ice model and an Earth model that looks something like this, okay? That only varies with depth. So this is where the primer starts. So yesterday I talked about sea level changes when ice sheets melt rapidly. Okay? But now let's take a step back and think about the Ice Age. The last million years of the Earth's history has been characterized by a series of glacial cycles, each with a period of about 100,000 years. Right? We have Peter Clark here, who's I still think has the most convincing explanation for the change from 40 to 100,000 year timescale of those glacial cycles. Each of those cycles had a 90,000 year growth phase, followed by a much more rapid deglaciation event. Glaciologists might even call it catastrophic 10,000 year deglaciation. The last such cycle ended 10,000 years ago. But the Earth is viscoelastic, so sea level continues to change, even though the ice stopped melting, in large part, 5 or 10,000 years ago. The system has viscosity, so it's still flowing. It's slowing down in its flow, but it's still changing. It's still deforming, and it's still, the sea level is still changing. So what this is a numerical prediction of the present day rate of change of sea level due to what stopped happening on the Earth's surface, in a sense, 5 to 10,000 years ago, the end of the last deglaciation. So here we are 5 or 10,000 years later, we still have these sea level changes. So this is where the primer is going to focus, okay? So let's think about this. We'll break it up into what we call near-field regions, regions close to the ice sheets in the dark red here, and the blue. These colors, by the way, are well off the scale of the plot. This is in millimeters per year. That blue reaches values of 3 or 4 millimeters per year. You'd be down the hole that way. These reds reach a centimeter per year. You'd be well outside, okay, close to where we were just sitting. Sort of funny, the sun came out, and I realized that everyone here then runs outside. We had 2.5 minutes of sun, right? That's the limit. That's what the Surgeon General tells you should be your limit, I think, right? Okay, so let's break this up and try to understand what's going on here. Where are all these colors coming from? Well, let's look at the near field. Regions that were once covered by ice, like Laurentia, Canada, northeastern United States. Antarctic was covered by much more ice. Scandinavia, Scotland, etc. Those regions are experiencing post-glacial uplift, or rebound. That's a term you would have all known, right? You had an ice sheet, it melted, the crust began to uplift. And remember what I've said, sea level is defined as a distance between these surfaces. If the crust is uplifting, beaches are uplifted, sea level is said to be falling. So this large-scale sea level fall, which reaches a centimeter per year, 10 times this scale, right, is associated with crustal uplift, post-glacial rebound, as you've heard. So you cannot go to anywhere, Fennoscandia, Hudson Bay, wherever, without seeing clear evidence of this. Even a geophysicist like me who spends very little time outdoors can look at uplifted beaches and recognize something is going on. And I'll show you some pictures of that. This rarely comes out. I was just corrected. This is sort of an interesting thing I'll mention. This was a photograph that was taken by Richard Alley when he's seen 2 of my talks, neither of which you could see what was going on here. He said, this is a better one. This is an island off Greenland covered by an ice sheet. The ice sheet melted, or a glacier melted. And then what happened is the crust began to uplift. A beach was formed. It continued to uplift. The next beach was formed. And then you get this pattern of parallel strand lines. The great Canadian geologist who worked in Hudson Bay used to call these flights of raised beach terraces, right? So that is a pinpoint observation of post-glacial rebound or uplift causing a local sea level fall, right? This is taken in Hudson Bay. You can't see it. And I was giving a talk recently, and a stratigrapher, one of my former students, so I was quite peeved, corrected me. I often said, these are uplifted beaches. And she said, no, they're not. There's stratigraphy that's been uplifted by the crustal uplift of Hudson Bay. The beaches are down here, right? But anyway, I said that we could talk about it after the talk, and then I chewed her out. Okay, so that's in these regions. But what about these blue regions? And I should go a bit faster now. What about these blue regions? These are the so-called peripheral bulges. When you bring an ice sheet onto a crust and you cause subsidence, the edges around the ice sheet, the periphery, bulge upwards. Think about just putting your hand in a tennis ball with your thumb in. You will cause bulges around the location of your thumb. In the same way, an ice sheet that depresses the crust will cause these peripheral bulges. And just like this region is post-glacial rebounding, those peripheral bulges are subsiding. And as they subside, sea level rises, local sea level rises, right? So all of those blue regions that you see at the periphery of these regions of post-glacial rebound are the peripheral bulges that are subsiding, like the US East and West Coast, for example. You're on the peripheral bulge here, right? those regions are subsiding, and therefore local sea level is rising due to this effect. And that gives you a hint of why these sorts of figures are so important. Computing this accurately is extremely important in modern climate research. You cannot go anywhere on the Earth's surface and make a sea level measurement and associate it directly with melting of polar ice sheets. Today, you have to correct for this. The US East Coast is experiencing 2 or 3 millimeters per year sea level rise because of this effect. Has nothing to do with modern melting. If you were to go to those sites and assume that the 5 or 6 millimeters you saw was entirely due to modern melting, and you didn't recognize that at least half of it's associated with the natural effect, you'd get your globally average sea level estimate totally wrong, right? So that's why these are so important. But now let's look at this far field region, okay? So these is the near field, rebound, peripheral bulge subsidence. What's causing this kind of long wavelength sea level fall? And that's this paper where this figure is taken from was focused on that sea level fall. A sea level fall of about 0.5 millimeter per year, right? Doesn't sound like much, but adds up to a lot, as I'll show you, right? So what is causing this bend away from sea level, away from the ice sheets of sea level fall of 0.5 millimeter? That's a process that we call equatorial ocean siphoning. What happens is you have these bulges that are subsiding. As they subside, it creates accommodation space for water. Water has to flow in to replace the area of these bulges that have subsided. So as on this cartoon, the subsidence causes the crust to subside, water flows in, and you may be 10,000 kilometers away, you're going to see the level of the water drop. The analog I use is a swimming pool. If you're in a 50-meter long swimming pool, you take a submerged object out of one end of it, you might be wading at the other side, you'll see the surface drop. And that's what this is. This is an island. Well, this is a geophysicist version of an island. Looks like an Apollo lunar capsule, doesn't it? Not even connected to the land. I didn't even bother to put a little stick there. But as that sea surface drops, what you're going to see is a local sea level fall, and it's about 0.5 millimeter per year. It's going on today because of the last glacial ice age, right? Okay, there's one other effect here that I'll only mention briefly. You notice that over continents, and remember sea level can be defined globally. So sea level fall is exacerbated. It's a little bit higher amplitude than it is over the oceans. And the reason for that is from 20 to 5,000 years ago, you dropped 120, 130 meters of water onto the oceans. You loaded the oceanic crust. So if you think at a shoreline at the interface between ocean and continent, you've loaded this with 120 meters of excess water. You will produce subsidence at the edge of that zone, uplift at the margin. You're literally flexing the continents upwards, and that's what you're seeing there. Right? And that's important in the history of ice age research. All of this stuff was worked out well before the models were worked out. People like Dick Walcott, who's now in New Zealand, used to be in Canada, worked all of this stuff out just by looking at the geological evidence well before the models had shown anything like this. Right? So now we think we understand this, right? This is siphoning, a movement of water towards the bulges. This is peripheral subsidence and uplift. So that's, oh, I wanted to show a picture of siphoning. I showed this picture yesterday when I was talking about modern sea level, and I said these are these so-called 3-meter beaches, and I didn't really explain where they came from. Well, they come from that process. Sea level's been falling 0.5 millimeter per year. The top of these corals, this is a dead coral now, there's live coral underneath this, but the top of this is 5 meters above sea level, 3 meters above sea level, and it's about 5,000 years old. So what happened here, ice sheets melted, sea level rose as the ice sheets melted. Once they stopped melting, this process took over of a sea level fall of 0.5 millimeter per year. And 0.5 millimeter per year for 5,000 years is 3 meters. So you'd hardly believe, sunning yourself over here at this beach, that this process, that this uplifted coral, as you would have called it, was due to an ice age effect, something that was happening 10,000 kilometers away. But it was. And in fact, for many years in the quaternary science literature, people described this as being a result of thermal tectonics, the plate going over some sort of hot region in the mantle. But that's not it at all. This is just a simple ice age effect. It's actually that picture is taken there. Right? It's that 0.5 millimeter per year adding up. But there's one other effect, and I talked about it yesterday, that I haven't included here, that's not important today, but it would be important during a period in which the ice was melting, and this was this gravitational effect. So these predictions are done today when ice is no longer melting. But let's say you were in a period from 20 to 5,000 years ago when ice was significantly melting. You would take this kind of field and you would to add to it the kind of physics that I talked about yesterday. And I won't go through that, even though some of you weren't there yesterday. There is another effect associated with the gravitational and deformational effect associated with the ice melting itself. That's not included in those other maps because we're looking today. Okay. So now so we've had this primer. We know about postglacial uplift, peripheral subsidence, this ocean siphoning, etc. Now I'm going to look at a problem, an iconic problem actually in Ice Age research, and that is the inference of ice volume at last glacial maximum based on Barbados. Here's the thinking. We want to know how much ice was locked up into the large continental-based ice sheets at last glacial maximum 20,000 years ago, the last time the ice reached its maximum extent. Okay? How much ice was there relative to today? One site has proven to be extremely important in that issue, in answering that question, and that's the Barbados sea level curve that was collected by Fairbanks, Bard, and others, and improved over the last few decades. This is a coral record of sea level change dating from the last glacial maximum on. The idea has been in the literature for many years that this is a perfect place to go because it's just so far away from the ice sheets, it's very little effect other than just what they call, the term they used was a dipstick for sea level, that you have this meter stick out there, or yardstick, I guess, in the US, right? And sea level goes up, and it just magically measures some globally average sea level change. You needn't worry about everywhere else. Just go to Barbados. It will give you what you want, right? Okay, that sounds like a tourism office advertisement. And here's why people thought that. This is the black line here is a actually very well-known numerical prediction. So you take this model I talked about. You have an ice sheet. You have a model for the Earth's structure that varies in depth alone. You run it, and you change parameters until you fit that record. And that's what that black line is. That's a prediction based on a very well-cited ice history and one-dimensional Earth model. And it fits the record marvelously. Okay? Some of these are upper bound, lower bounds, etc. So it goes through that record. The red line here isn't the prediction. The red line is that eustatic change. It's me saying, I'll take all the ice that melted, and I'll just melt it and uniformly distribute it. How much would sea level rise in that case? And the fact that the red line tracks the black to within 2 or 3 meters, actually, is an argument for why this is such an important site. Go to this site, and you don't have to worry about all this dynamics. Just look at the corals, because they're telling you what globally average sea level was. Okay? But this has been debated and has become more and more controversial over the last 10 years because other sites, particularly in Australia, Bonaparte Gulf in the northern part of Australia, show that the peak ice volume wasn't equivalent to 120 or 122 meters. It was more like 130 to 135. And that may not sound like a big difference to you, 10 or 15 meters. But remember, West Antarctic would give you 5, Greenland. These are large differences. Right? You're talking about large ice sheets. If it 135 relative to 122, and I'm going to make an argument to you that it was 135, at least 130, that raises very interesting and perplexing question of where was all that ice? Because efforts to inventory the ice don't get you that much ice. Right? So these kinds of studies led to the conclusion that in a globally average sense, at LGM relative to today, there was equivalent of 120 meters of excess ice in sea level equivalent units. Okay? But here's the problem with that. Well, yeah, no, I'll skip over that. Here's the problem. This is a very tectonically active area. Okay? This is not the place on the Earth where you'd want to assume that things only varied with depth. Right? You have the Caribbean plate here. One of my group members actually writing a paper on an idea that Walter Alvarez had for the development of this oceanic plate, but that's another story, another time. But you have the South American plate subducting under, this is the accretionary prism, subducting under the Caribbean plate. and Barbados is there, right? So Barbados is in a location that is underlain by a slab that is subducting below it, right? So let's look. So now I'm going to, just as a thing, I showed you this picture yesterday. I've talked about Natalia's work on rapid sea level change. The work I'm about to tell you is Jackie's work here, the other freezing graduate student in Greenland. Because what she recognized right away was that perhaps the assumption that the Earth was an onion, you could just peel off these radial layers, was not correct in Barbados. Maybe we should do something a little better here. We should take into account what people like Isaacs, Oliver, and Sykes told us in the late 60s, that plate tectonics had a three-dimensional structure. We needed to include that, right? That was her idea, 100%. And so what we've done now, this is a little bit tougher to explain. I'm certainly not going to get into the details of it, is we've just thrown out those old models, those one-dimensional models, and now we run ice age models on large finite element grids. This is a grid that has 24 million elements. We solve exactly the same equations as we've always solved, except this grid allows us to incorporate variations in structure within the Earth's interior, right? So we can get away from this onion model of the Earth, and we can include some of this realistic complexity in the Earth's structure, right? This is all work done by a research associate in the group, Constantine, and this gives you, it's really amazing what he does. This gives you a kind of sense of the surface of the slab as it's descending under Barbados. So he's incorporated those ideas. Here's the model as we set it up. So we've tried a different model of Barbados. This is a model taken from Malcolm Sandbridge's work of the slab in this area. This is showing you as a function of depth its location. So what you're seeing is the slab is descending under here. It actually stays very shallow for quite a while and then it deeps steeply so that it's got a depth of about 600 kilometers by the time it reaches that leftmost area. All right. So that's a slab. We've placed the slab into this system. We also have varied the thickness of the plate, this lithospheric plate that I've talked about it. This is a Guyana shield here, and seismic tomography indicates that that may be as thick as 300 kilometers, rather than the typical 100 kilometers that's used in these onion skin models. So we include this, and sorry, this of course doesn't come out, but this is just to tell you that we also include structure at the deeper parts of the Earth's interior, right? So what we're going to do is take this model now, run it on that finite element code, and what do we get? Well, we get a very significant change in the physics of sea level, right? This is a map that's showing you the difference between this more realistic model and the onion model, one-dimensional model of the Earth. The differences in your estimate of excess ice volume at last glacial maximum. And these can easily reach things, this is well off the scale of the plot actually, so up to 12 meters, 13 meters or so. This is Barbados, it's in an area with a strong gradient in that signal. But there's Barbados, and this is not zero. Three-dimensional effects are extremely important in this area, which perhaps isn't surprising if you remember lessons from plate tectonics. But in the Ice Age, this was all forgotten for decades, right? The blue line here just represents, as a function of the time, the difference between the three-dimensional model and the one-dimensional model, right? So it's incorporating, and what this means is the following. I'll give you a kind of physical description rather than point to lines which are hard to understand. Although the maximum effect reaches, in this particular calculation, 8 meters at last glacial maximum. This is the last glacial maximum. This is the present day, okay? So what's causing this change? What's happening? Well, this is an attempt in a cartoon style to tell you what's happening. Here's a case where you've included the slab that's descending under Barbados. Here's a case where you haven't. 1D versus 3D. You've got some water level here. This is last glacial maximum. You melt a ton of ice, and you increase the water levels by 120, 130 meters. When you do that, typically what will happen is, because you've added this load, is the crust will subside in consequence of that load. The difference here, though, is that you now have a slab that has very high viscosity. A typical slab viscosity is 2 orders of magnitude greater than the surrounding. You've into the upper mantle just stuck this high viscosity plug that resists deformation. So what will happen is, instead of an ice depression of this crust, wherever the slab is will mute that depression, right? You will have almost no crustal subsidence. It's quite impressive, right? How little the crust will subside when you stick this slab from a subduction zone, right? So here's what Jackie came up with. So here's the old case. Here's the original calculation with the original eustatic level. But now this calculation has three-dimensional effects added to it. And because the crust is muted, the crustal deformation, the sea level change you predict is less, because you're not allowing those surfaces, the distance between those two surfaces to increase. So you're muted by up to about 10 or 12 meters. In this particular case, it's 8 meters. So now you don't fit the data anymore. Now this ice model that used to fit the data is too shallow. It predicts too shallow a sea level rise. The only way to fit the data again is to increase the ice in your model in order to bring this blue line back down to where you need it to be to fit the data. So that muting of the sea level rise by the slab means that you have always, for 3 decades, underestimated the excess volume at last glacial maximum by 10 meters or so. The moral of this story is that the sea level rise associated with that, well, the eustatic sea level rise was at least 130. So all those studies based on the Australian data were correct. And the kind of classic studies that people cite all the time based on Barbados were incorrect. They didn't take into account this subduction, the three-dimensionality of plate tectonics. And I think there is no argument anymore, and or a better way to put that, a more positive way, is that there is now consensus in the literature that the excess ice volume was equivalent to at least 130 meters. And this is important because there have been a series of studies over the last few years that have really made this quite enigmatic. What we're saying here is that there was 10 meters more of sea level locked up into ice sheets at last glacial maximum. The same studies that were giving you 120 had very large Antarctic ice sheets. The Antarctic itself contributed up to 25 meters of that 120. But recent simulations of Antarctic ice volume at LGM suggest that it was much smaller than this. So not only has the total number gone up, the Antarctic contribution has gone down, which means there is a whole lot of ice that's missing. And it's anyone's guess. What typically happens in the Ice Age literature that I'm involved in is people start looking around to put ice in places where they can hide it, right? They'll put it over the prairies of Canada. They'll have this huge dome of ice there because there's very little data that would disqualify that. They'll put it in the East Antarctic. They hide it. It's a well-known thing in the Ice Age literature that we're forever hiding ice, right? But there's no hiding this much excess, right? You now have probably 30 meters, almost a quarter of the total that's unaccounted for in inventories of global ice volume, right? Though, Peter, you might disagree with that because Peter knows much more about global distributions. I wanted to say something, just a couple of overheads, which chatted at lunch about this, about how all this sort of more highfalutin modeling helps in other applications. One in particular that we've become involved in is the timing of the Black Sea flood. I'm not going to go in any great detail here, but some of you may know that there's a question started by Bill Ryan at Lamont, a suggestion that there was a cataclysmic flooding event from the Mediterranean to the Black Sea that is the origin of the flood legend, right? And so this, as you can imagine, has garnered significant interest, and people talk about it, and they're trying to control, geochronologically speaking, when that flooding event happened. When was the Bosphorus sill breached? And I just want to show you one calculation to show you that even in a location like this, these three-dimensional effects become very important. The typical Ice Age calculation is shown here. This is this onion skin calculation. It reaches sill depth, or reached sill depth, about 9,000 years ago. So this calculation would tell you that you got high enough to breach this about 9,000 years ago. But the data, the geochronological data, suggest at least 2,000 years earlier, right? Although there's a lot of disagreement. I'll be agnostic about it, simply to show you how important these effects are. But this is a location that, if you know some tectonics, you realize this is even worse than Barbados, right? This is a highly complex tectonic environment. This is an image of the tectonic plate system. Actually, Jason Morgan and I just had a long discussion about this. And this is a very famous plate system. This is called the watermelon tectonic system. I don't know if any of you have heard of this, but this is the Arabian plate, and I'll show you later why, but the Arabian plate is being thrust northward. As it is, the Anatolian plate is spat out sideways, and people talk about it like a watermelon seed being squished, and out it pops, in this case to the west, producing these horrendous earthquakes on the North Anatolian fault, right? So here's the Bosphorus sill, right? This is a highly complicated tectonic environment. I want to show you an image just published a few months ago in Nature Geoscience from a group at Princeton that looks at high-resolution images of seismic structure in the Earth's upper mantle. I see Anna back there. We were talking about these methods. These are these new methods called adjoint tomography methods that are getting resolution of mantle structure order of magnitude better than it was a decade ago, right? And I just want to point out, I'm not going to go through this. Some of you will know this is the Tornquist zone, etc., who know some of this. Let's see. I'm even having trouble. There's the Black Sea, right? So this is at a depth of 175 kilometers. Blue means seismically fast and therefore cold. Red means seismically slow and therefore hot. So you see right at the location of the sill, you have a transition from a region that is cold, fast, to one that is more average. There is a lot of structure under there, and you can see that even more if you take a cross-section. Unfortunately, this is a cross-section that doesn't go through the sill. It's a bit northerly, but you can see that that heterogeneity extends well through the mantle. And again, this was only a 2-minute digression, but here's an example now of doing that same calculation that was done, right? Oh, I've switched the two, unfortunately. This is the new one, not the old one. But the shift in the timing of the breach of the Bosphorus sill is 1,200 years just by including three-dimensional effects, right? So these ice age calculations are really strongly perturbed in zones like this. So even in areas of archaeology where they've become central tools in archaeological exploration of these issues, there's a larger uncertainty. People, even a few years ago, would have said that the original calculation was good to 100 years. And here we've shown there's a bias that's over a millennium. Now I'm going to go to something that's near and dear to my heart. It's dynamic topography. It's what I started working on as a graduate student. This is the uplift and subsidence of continents and oceans associated with mantle flow. I saw Peter look at his watch for the first time there. So, okay, this is a picture taken from Strike Valley. These are old shorelines, uplifted Cretaceous, I've already shown you by bias by saying they're uplifted Cretaceous shorelines. This was when I started graduate work in the mid-'80s, this was where it was at. It was looking at these sorts of things if you were in tectonics and saying, well, what happened? Did the water go down or did the land come up? The whole debate was called eustasy versus eporogeny. The geologist always, with these terms that nobody understands, calls it eporogeny. The geophysicist called it eustasy, right? That's a pretty good template for that debate, right? And the great geologists, Sloss, Speed, Dickinson, for those of you, they understood this was the continent going up, right? It was not the water going down. They were able to discriminate on the basis of the stratigraphy of those two things, right? But nevertheless, it was a debate. What is happening here, right? Well, it gets even muddier, right, when you take a global look at what the Earth's hypsometry was like in that period. You know, this is a map from Blakey. It's obviously done to show you just how immense the flooding was at the same time globally. And that picture, or one like it, was largely why the bias entered the literature that it was a global sea level rise or fall. So you can't look at that plot without thinking, well, sea level's up everywhere, right? And you'd be wrong, right? Global average sea level at this point in time was lower, not upper. This is all a dynamic topography effect, as I'll show you, right? There's the Western Interior Seaway. In fact, I have a graduate student looking at tides in the Western Interior Seaway by running a tide model. But let's now ask and try to answer this question. This is the second paper I wrote as a graduate student. It wasn't my idea, although I take credit whenever it's worth it, right? It was the idea of my supervisor at the time, Chris Beaumont, who's at Dalhousie. I don't know if Chris has ever been here, a lithospheric deformation modeler. Chris called me up, pre-internet, and said, I have an idea, and you do mantle modeling, and I just ran the model. And the argument was as follows. Why did we have the Western Interior Seaway? Geologists like Sloss Speed, for those of you who know this literature, were saying the continent went down, we don't know why. But most people said it was a global sea level rise that caused this inundation everywhere. But one thing Chris had noticed was that the seaway existed only when subduction existed on the West Coast. As soon as subduction ended, the seaway disappeared. He was able to correlate the history of subduction off that coast with the sea level on that coast. And so we came up with the following model that's actually not particularly relevant to the West Coast, but it's a subduction model, right? You can imagine that what happens is subduction starts off some otherwise stable continental region. As that subduction continues, right, viscous stresses pull the overlying continent down. I'm not even sure what the analogy is. Imagine, I was going to say a bucket of tar, but very few of us have seen a bucket of tar. But imagine a bucket of tar. Just go with me for a minute. I can't think of any other. Canadian maple syrup. Imagine a bucket of Canadian maple syrup, and you drop an object that descends. Even when that object is halfway down, this priceless maple syrup, the surface will still be buoyed downwards by viscous stresses. As it gets far enough away, it'll come back up. The idea is exactly the same here. As you have active subduction, you brought the continent down, you flooded it. When subduction ended, it popped back up, and so did all the sediments that had accumulated all that time. So this was what was known as dynamic topography. So it was the two papers published within 2 weeks, both claimed that they came up with the term. Right? So this is just to give you an idea of the large spatial scale of this problem. These are essentially sediment thickness maps, how much sediment was dropped down in the Upper Cretaceous, and you can see from the middle part of the continent out to the west, you have this wedge of sediment that increases to the west. Well away, by the way, from the trench and from the foreland basin, for those who know a lot about sedimentary basins. You could filter out that foreland basin, you see this long wavelength effect. And this is the present-day topography in a picture from 1989, but it increases to the west. So what happened here is the continent was brought down, sea level flooded in, subduction ended, then the whole thing got popped up. Denver's not a mile high because of the Rockies, right? Denver's a mile high because the sediment package that was pushed downwards, or the crust, popped back up, and with it did all the sediments, and so did Denver, right? Denver's too far away from the orogeny to have been affected that much, right? So this is dynamic topography, and this is looking at it in cross-section. AA prime, the basement went down, here's the foreland basin, this filled with sediments, subduction ended, and it popped back up. But I showed you a picture here that wasn't really relevant to the West Coast, right? This was, what would you call, this was the cessation, geophysicists would say, cessation of subduction due to the accretion of a continental terrain. Subduction stopped because you can't subduct the continent, right? But that's not what happened on the West Coast. Even a basic course tells you that this is what happened on the West Coast. This is from Tanya Atwater, I just met a few months ago, actually. So we had the Farallon plate here. As the system, you had a large subduction zone across the whole of the United States. Once you began to subduct the ridge between the Farallon plate and the Pacific plate, you developed the San Andreas Fault. But effectively, you ended subduction across this whole region, right? Subduction ended because you essentially subducted the whole ridge. Let's try that one more time, just to give you a sense. So in my classes, I talk about analyzing the evolution of the Farallon plate. But this is a two-dimensional view. Think of what's happening in 3 dimensions. You've ended subduction here. That slab that was subducting here is now just descending into the mantle. And we see it. I'll show you an image. Seismic tomography sees the Farallon plate now, which stopped subducting 30 million years ago, is now in the middle of the mantle, in the lower mantle, and you can see it very easily with seismic tomography. Again, an example of a 3-dimensional process. That's why subduction ended on that coast. And I won't belabor it, But that tilting is easily explained through the process that I've talked about, that long wavelength tilting. In fact, it fits because the steeper the subduction angle, well, I guess that's the shallower the subduction angle is. I always reverse that. The shallower the subduction angle, the longer the horizontal wavelength of this sedimentation. To get this sediment into the middle part of this continent required a subduction at an angle no greater than 30 degrees. And that fits the volcanics. Right? There's evidence for that. Right? When I was in Canada, I used to try to name the states here, but nobody would know the difference. But I was talking to the students at lunch, and I told them a story. I won't repeat the story where I thought Delaware was in the deep south. And so that gives you a good idea that I will stay away from trying to name those individual things. Now I'm just going to give you a quick survey through dynamic topography. All of these regions boxed up here represent regions in which dynamic topography is now seen to be the main driver of topography. So we've seen this. I'm going to talk to you about the US East Coast. This is a particularly important place because there's no subduction zone there at all. There's no plate boundary whatsoever. It's called a stable continental platform. But I wrote a paper with a postdoc that's called There's No Such Thing as a Stable Continental Platform. And I'll show you, even though there is no subduction zone, no plate boundary there, this region went up over 100 meters in the last 20 million years. I spent a lot of time, so have many people, looking at these regions. The uplift of South Africa. Southern part of Africa is over, well, 3/4 of a kilometer on average higher than the northern part. You can just see that, right? You don't have to do a great analysis. That's dynamic topography. I'll show you, I hope, a map of that. There is a large-scale structure in the Earth's mantle that is coming up under this region. It's called a megaplume or a superplume. It depends on who you talk to. There are all sorts of terms for it. But a large, hot, thermally buoyant upwelling that's coming up and pushing southern Africa upwards. It then kinks towards East Africa, and it's the reason why you have the East African rift. It's tearing the continent apart. And then it comes up under the Afar here, the triple junction that's there, and it throws Arabia sideways. This is so, well, I shouldn't say it's energetic. I sometimes get overwrought about these things. It's still only coming up sub-millimeter per year, right? But it's causing, this one structure is causing the uplift here, the rifting here, the tilting of Arabia. It's also causing Arabia to be thrown, let's hope that's only temporary. Oh, it's asking me if I want to connect. That's all right. Causing Arabia, when I talked to you about that watermelon seed coming sideways, this same structure is the thing that's thrusting Arabia upwards and forcing the Anatolian plate sideways. All of these are dynamically driven. Oh yeah, I did show, great, I added this. This is that structure I was talking about. This is the way seismologists see the Earth as a shoebox, right? And this is Africa. This is this large-scale structure. There are two of them. There's another one under the Pacific, and some people have started calling them Jason and Tuzo, which is sort of silly. I'd want something better than a hot blob named after me. But it's coming up, causing this uplift of southern Africa. It's impinging on the African continent towards the east and doing all of this other damage, right? You know, the old debate in the early plate tectonics world, how did you break apart a plate? And little did we know that there was a great example of how you break apart a plate sitting in front of us. It was East Africa. Okay, so now I want to talk about an application of all this work, the Pliocene. 3 million years ago, how high did sea level get? And we'll talk about this. So this is an oxygen isotope stack from Lasique and Raymond, the one that everyone refers to. 3 million years is the end of what's known as the mid-Pliocene warm period, or climate optimum, a period of relative warmth. We came out of this into sort of obliquity-driven ice age cycles and then into a 100,000-year ice age cycle. The question is, you were warm, and you were warm for a very protracted period of time there. And there's all sorts of analogs. Temperatures were elevated at that period, 2 to 3 degrees Celsius. Estimates of sea level at that point, just before you entered into this more vigorous ice age, were 25 to 50 meters above present. Right? And that was the problem, right? Because to get 25 or 50 meters, you would have had to melt the West Antarctic, Greenland, and a significant portion of the East Antarctic ice sheet to produce the 50-meter sea level rise then, right? So the question is, what happened there? Well, I've written several papers in the last few years to show to argue that it isn't a eustatic sea level rise, at least not largely. This is I won't talk about this in detail. It's a paper I wrote with Moremo and colleagues that said that there's one thing that you should have corrected that 50 meters for that you didn't, and that is the Ice Age. This area of, I forgot to say that this 25 to 50 meters is largely taken from the uplift of a feature that's known as the Orangeburg Scarp, a 3 million year old feature or shoreline on the east coast of the United States. And so the first paper, which I won't talk about, but you'll understand now, this region is on that peripheral bulge. Sea level is rising there, which means that land is lower than it would normally be, and sea level is rising to get it to its equilibrium elevation. That correction is, in this model, 20 meters. So right away, you take that 25 and 50 and say, you forgot the 20 meters that's caused by this Ice Age effect. But I don't want to talk about that today. I wanted to talk about dynamic topography. And this is the paper that argued there's no such thing as a stable platform. And this is a more recent paper published just a few months ago by Dave Rowley, University of Chicago, and a group that included me, that made the argument that over this 3 million year period, we have to consider dynamic topography. We have to consider mantle flow and what it's done to the elevation of the continent before we can interpret that elevated shoreline as a eustatic feature, right? So I'm just going to go through, it's not really technical, but I at least want to give you a background on how you do these kinds of calculations. In the old days, in '89, when I was a graduate student, right, you didn't care about seismic tomography. It was in its infancy. Your slab was a perfect rectangle that descended into the mantle. You can't get away from that, away with that anymore, right? You have to do something more sophisticated, and you use a seismic tomographic image. You start with an image that tomographers give you, in this case of some % variation in the speed of seismic waves. You take that image, which for a geodynamicist is interesting but not useful, because what drives flow is buoyancy, not seismic wave speed. So you have to convert that to density. You take these blues and reds and you convert it to density. And you do that by using scalings that mineral physicists come up with. They take mantle materials, stick them in between two diamond heads, twist them up into high pressures, and you determine how density will change with seismic velocity in mantle materials. So you make that scaling. So that's the first thing you do. But now density is what you want, but you also have to compute flow. So you take that density and you run a flow calculation, just a convective flow calculation. You need in that a viscosity, so I'll give you one, right? But there's several people who would give you one. So now you've got all the elements. You've got density, which is buoyancy, right? How much buoyancy in the system. And you've got viscosity, which tells you how sluggish or not the flow will be associated with that buoyancy. And you run that model. And let's go quickly through that. So I'm going to run a model. Here's a seismic tomography model under North America. This is the same model, two different images to try to give you an idea of what's under there, right? What's under there, this big blue stuff, that's the Farallon plate. That's the plate that caused the tilting of the western part of the North American continent. It now lies at about 1,000 kilometers depth under the eastern part of the US, okay? And it's lying that far east because, of course, North America is riding quickly over the structure, right? These green lines already tell the tale, in a sense. They're calculations of the flow associated with it. This is a cold, high viscosity, dense slab that is descending and it's driving flow. And there's also this active upwelling, a red region of hot upwelling material that overlays it. And that upwelling material is actually the most important part of this. So what I want to show you now is a movie, right? So now we take that snapshot, because seismic tomographers only tell us what's there today. We run those simulations, but we run them backwards in time, okay? I'm actually going to reverse the image so we're going forward in time. But you start today, you fit all the data you can with these models, and then you run it backwards. And you compute how continents and plates are moving when you do that. So here's an image under North America. This is a very famous place to take data. Sequence stratigraphers come out there all the time. And they assume it's a stable platform, right? So all of that oil research that was done off the East Coast here assumed this was stable. And so this movie, in effect, is going to show you just how wrong that assumption is. We'll see as a function of this 30 million years what happens to that continent. And what you'll see before I show you the movie is this thing just uplifts because of that hot upwelling there. And this stuff further into the interior comes down because of the Farallon plate. That's the Farallon plate. That's the upwelling. Well, let's see the movie. I'm excited because this may be the only time it's ever worked. Okay. Or maybe not. Oh, yeah, there it is. So these 25 million years ago, 20 million years ago, 15 million years ago, you start seeing this dramatic uplift, this upwelling underneath this region. This is a passive continental margin, and yet it's moving upwards. This area has moved upward 300 meters in 30 million years. Right? The Orangeburg Scarp is here. It's being influenced significantly. That scarp, which on average is 50 to 80 meters high, I've already told you, is affected by the Ice Age. It's also affected by this structures, right? Huh? Let's look at that point, actually. Here's that specific point, the New Jersey margin, as a function of time over the last 30 million years. This is sea level. Sea level is falling because land is going up. Land has gone up on New Jersey by over 100 meters in the last 30 million years, right? And this really flies in the face of so much work on passive margins that assume that all you have to worry about is subsidence as they move away from the ridge, right? Compaction and things like that. No, you have to worry about the mantle here. There's no place that you're going to be immune to these processes. And now I'll show you the result from the paper. So now we've run that code, and we've looked at this shoreline, and we've said, okay, we have the present-day shoreline. We have this sea level change we've predicted. Where does the shoreline go? Where would it have been 10, 15, 20, 30 million years ago, right? I think I only showed you where it was 30 million years ago. Here's just an image, a geological map. I always forget where the Orangeburg, this, I hope, is the Orangeburg Scarp. Yes, I think that's right. It doesn't matter. We're looking over this area, and now this is superimposed on the Scarp location is a prediction of the change in sea level over the last 30 million years. So this is just one snapshot of the video I showed you, right? But now we apply this to the topography or the hypsometry, as some people call it, there, and we say, well, how much would sea level have changed from its present location? And does that match the location of the Scarp? Because the Scarp is the shoreline, right? And when you do that, you see that the match is actually pretty impressive, right? So particularly in the north, there's misfit in the south. But here's the prediction here in this white, right? No, I'm sorry. The prediction is here between the gray and the white. And these line is the location of the Scarp. So you move it from where it is today, and you certainly match in the north. There's mismatch in the south. But even if you don't believe this story, you recognize there is something going on here. Dynamic topography is driving this uplift. And so now the IPCC published a report on paleo sea level, and Peter was one of the lead authors on that sea level chapter. And I guess you can relate to everybody just how people were sort of knocking at each other over it. People want to say something about the Pliocene. And I guess it's maybe as history of science we think of this, but my view, which is not a very popular one, is it's too early. Shut up, right? And I don't mean to be silly about it, but there is so much uncertainty associated with the Ice Age, so much uncertainty associated with dynamic topography. We cannot really say how much of what we see, that uplift, is due to melting of ice during the mid-Pliocene warm period. You cannot say it. There are too many uncertainties still. And unfortunately, those uncertainties are going to take a long time to work out of the system before you can rigorously say anything. The better thing to do, I might add, is to leave this area, because this is particularly contaminated by Ice Age effects. And so I'm involved in several studies that are led by a fellow named Alessio Revere and Mo Ramo called Pliomex, where the suggestion is two better places to look, as in southern Australia, this sort of Great Australian Bight, and southern Africa. Now you might say, well, wait a minute, you just told me southern Africa was uplifted. But there's no evidence that that uplift has continued in the last 3 million years or so, where you'd be interested in this. That uplift seems to have stopped, although there's some people who just yell at me for saying that. Right? But there are places you can go that are not strongly contaminated by the Ice Age, a little, because remember that map I showed you of Ice Age sea level? It's a global map. You still have to take into account Ice Age effects here, but they're much smaller. And you still have to take into account dynamic effects here, but they're much smaller associated with mantle convection. Not at all time. I wrote a paper with a graduate student that talked about the development of the Karoo Basin, which is a much older basin here, when there was active subduction there. And that's really the end, but I want to show one picture more for Peter's benefit, and that is, and Anders as well there. I want to show you that dynamic topography can make a very strong connection with ice sheet stability, and you think, that's just crazy, right? But it's true. This is a great example. This is work of Jackie's, that same cold graduate student in Greenland. That's because I wouldn't pay for a hotel. No, just kidding. A little joke. Okay? So the good news, as some of you learned yesterday, was that I said to you that because sea level falls near the margin of a melting ice sheet, the good news about that is that that sea level fall will act to stabilize the ice sheet. So I talked to you about that as good news, but unfortunately, I have some less good, well, that's an optimistic way to put it, right? Less good news, right? This is the dynamic topography change over the last 3 million years. Not over we can run that movie anywhere that we have seismic images, right? So we take a very well-constrained seismic model under the Antarctic, set it in that movie, run it backward in time, and we say, well, this region has experienced up to 500 meters. So that's the Wilkes basin, subglacial basin, I think they call it, right? So this is a marine-based sector of the East Antarctic, or it touches on a marine-based sector, right? I have the experts here. I feel I have to be careful, right? But over the last 3 million years, that region has gone up as much as 500 meters because of dynamic topography. And I should say, this fits some geological evidence in those areas. This is an area of active and large-scale uplift. What this means is that 3 million years ago, this area, this crust, was 500 meters lower than it is today. And when people looked at the Pliocene ice sheets at this time, they used present-day topography, right? And they ran a model of Pliocene climate, and they said, what did the ice sheets look like there? But now we're saying, well, you have to change that model because you have to perturb the topography by 500 meters here, lower, and here a bit higher, etc. So we take this, we add it to the topography, and we rerun those calculations, and we see, lo and behold, a far more significant, this is corrected for dynamic topography and uncorrected. This is a change. It's very hard to see there. This is a change. Where you had this uplift, where it was actually sitting a half a kilometer lower, you predict a difference that is a significant melt. So significant that you can ask, well, how much melt in meters of equivalent sea level rise, right? So here's what an old calculation would give you, about 12 meters, which is a typical calculation. It's actually, with dynamic topography, 15 meters of melt relative to present day, right? This is a 25% increase. And I love this demonstration because it shows that mantle dynamics has a direct influence on ice sheet stability. And who would have thought of that? Well, Jackie did. Okay, so these are my conclusions. I know I've gone long here. I won't read them, simply to say that understanding mantle dynamics is a two-pronged problem. The first, you want to understand it because it tells you something about the structure. It tells you where the high viscosity areas and the low viscosity areas are. And that's going to influence your predictions of sea level change. That's one area of research that I think is going to be very active in the next few years. The second prong is to treat it as a dynamic process. If you know the mantle structure, run that movie, because that's deforming the Earth's surface everywhere. It's not just limited to active plate margins, right? And that up and down motion can have direct impact, as I've just shown you in the Antarctic on ice sheet stability, or it can have an impact on the elevation of ancient shorelines. And you could then estimate incorrectly ice volumes that you would infer from those shorelines. So both of those fields need sophistication in the thinking of mantle dynamics. And this is just scratching the surface. To be honest, there's so much more that has to be done here. These dynamic topography models have a large scope for improvement. This is really early days in this field, but it's going to be a very active area of research, but not only in that small community that call themselves mantle dynamicists, but in a much larger community of people that call themselves climate scientists. So thank you very much. That was way over time. You've been really patient with me. You're lucky, though. It could have even been worse, right?
So do you think that you can go back and revisit the sequences of the soft sequences and of sloths or the Vail mission curves and reinterpret stratigraphy entirely forced by Mantle?
Well, yeah. Yeah, so partly, Sloss was one of the first people to understand that you could, so just imagine you have a stable continental platform, sea level rise. He argued that the stratigraphy you would see would be very different from if you saw this, right? You'd get wedges of sediment. So Sloss understood that if I had a long enough transect of stratigraphy, I could tell the difference between the two. But the one thing that you will 100% have to revisit are the inferences of Vail, Hack, the exxon curves of sea level. The long timescale exxon curves of sea level are completely contaminated by dynamic topography. The longest, I wish I had an image of this. If you look at sea level over the last 500 million years, this 100 million year cycle in sea level that you see of amplitude 100 to 200 meters, right? What people don't realize is everyone looks at those and thinks, well, that's a global compilation. Two sites, New Jersey, Northwest Africa. Both of them subject to significant dynamic topography. So all of those long timescale, not the short timescale stuff Vail and others saw, that was eustatic, right? The Mantle can't do things on 10,000 year timescales. But the longest timescale parts of those Vail curves or the exxon curves, in my view, show you nothing, say nothing robust about global sea level change. You're being fooled, right? But you can't go back to those because anytime I ever try to get the data, they won't give it to me, right? But that's okay. Well, they will, but you have to pay a significant amount of money to get those cores, right? But I think, to be honest, when I read those papers, at first I became a kind of a critic of those curves. When I read it, I don't think that was the focus of Vail and others weren't really focused on long-term sea level. That was something that they thought they could just get out of it. Their focus was somewhere else. And there are a lot of critics of sequence stratigraphy, right? There are a lot of people who argue the very idea of inferring changes in sea level, changes in accommodation space from patterns that you see through seismic cross-sections is faulty. I'm not an expert in that issue. I can only say that those sequences are going to be contaminated by dynamic topography. Yeah, Anna?
What happens with your boundary conditions?
Which?
I need surface sea bottom. And the reason I'm asking is because there's really two ways to get back, both in terms of topography and also in terms of water moving out of the mantle back into the mantle.
Oh, well, okay, so there's many issues that you raise, right? So the boundary conditions are free surface at the top and essentially a free surface at the bottom because you've got the mantle sitting on a liquid core. But I'll tell you why we think that those boundary conditions work. One of the things I didn't mention because it gets really to the depths of my kind of theoretical work, but I look at rotational anomalies in the Earth, right? And there is a very specific anomaly that is a function of the shape of the boundary between the core and the rocky mantle. It's called the free core nutation. And scientists have known for a very long time that measurements of that nutation require certain geometry of that boundary, and these models won't be run unless they fit that as amongst a bunch of others. So a simple free surface. Now, in terms of water becomes a boundary condition at the surface too, because your dynamic topography will depend on whether you're water covered or air. That's simply taken care of. But changes in water content into the subsurface, that happens, but it happens, this would perturb these amplitudes by, I am sure, less than a meter or so. I'm absolutely positive of it. Over these timescales, you're talking about a shorter timescale effects, but over long timescales, the effect of water on dynamic topography would be very small, and certainly less than a meter. Right? Any other? Yeah.
On the last point, in 1995, I wrote a paper suggesting that extreme uplift rates for this region were unlikely because there are relatively high concentrations of cosmic rays isotopes in the rock surfaces. And it's long enough ago that I don't remember 500 meters
Right, no, absolutely, right. So when I refer to the geological record in support of this, I refer to the record that somebody like me would look at, right, which is evidence of erosional outflux of material over periods of time. And those estimates place this at the lower bound. But yeah, so Anders, Peter, I mean, that's where you're going to have to do the kinds of studies that I'm sorry, I'm not familiar with your paper from '95, but to see whether there's consistency. It's consistent from estimates based on erosion, right? But I haven't looked at any other estimate.
Yeah, I mean, there was a big controversy about these geologic deposits that contain fossil leaves that presumably couldn't have existed at these elevations, but they've kind of
Well, it's certainly, one of the problems with these models, in some senses, to be totally blunt, is they're global. And the models do not always correctly predict uplift or subsidence that we know occurs. It's a global model with global uncertainties associated with the seismic structure, the viscosity structure, etc. On the East Coast, you had a nice test. Can you get the Orangeburg Scarp to be where it was? And the answer is quite clearly yes. Here, the evidence is far more limited, but I agree 100%. The ultimate test of these will be the whole host of geological and geochemical evidence you have for these events, right? Yeah.
The corridor area is also complicated by active tectonics
Yeah.
and rifting and volcanism that's been going on for
Right.
a long time.
Yeah.
Yeah, your map of the dynamic topography areas didn't have Australia separated out, and you mentioned Australia as a potentially more stable area,
Yeah.
I thought, to look at.
Yeah.
But hasn't Gurnis
Yeah.
talked about a lot of dynamic topography in Australia? Australia migrated very rapidly
Yeah.
northward. And there is this idea I've read about that the whole continent is tilted with that nullibar plain Miocene stuff
Yep.
uplifted. So how does that fit into your picture?
In too many ways to document here. It was the only time in my career I've ever written a paper, was about to submit it, opened up my computer and saw the same paper published. And that was Gurnis's paper. So I know exactly what you're talking about. Gurnis argued that there was this large translation of movement of the Australian continent over mantle structure, right? Over cold mantle structure. And what he said was, as it moved over that structure, it buoyed down and came back up. But the time scale is important here. That ended well before there. But however, so I don't think that the Gurnis simulation is a problem to argue for stability at present day. What is exactly what you said. There's evidence of faulting in the nullarbor plane. And so before you work out whether that's a stable region, you have to try to understand why there appears to be not so much active faulting there, but certainly recent faulting in the nullarbor plane. So there is two groups in Australia that argue stable, not stable, because of the very features that you mentioned. And I agree completely. I sort of whitewashed it. But that debate has to be taken into account before you would use that as a tectonically stable environment. But one way you can get around that, one way you can start to get to those issues, even from a modeling perspective, is the modeling shouldn't just tell you what the amplitude of the uplift and subsidence is. It should tell you what the geographic variation is. And it should be able to tell you that in an accurate way. And on the US East Coast, you wouldn't get that shoreline correctly unless its location, unless you very nicely matched the sort of up and down as you walked along the Orangeburg Scarp. The nullarbor plane is a little bit more complicated because it's limited, and therefore you don't have such a long transect to see that geographic variability. But where you can, that becomes an important constraint. But I agree with you completely.
Just one comment, and maybe this is something I should talk to you about afterwards, but in central Australia, there is a long-term history of river adjustment.
Mm-hmm.
This is over tens of millions of years, which is consistent with base level change going up and down.
Yep.
So base level, of course, you were talking about sea level.
Yep.
Base level for rivers is another potential way to look at dynamic topography.
Yep, sure.
And Australia being relatively stable but deformed, at least by the way Gurnis talked about it, is a particularly interesting place to look at that issue.
stop using that name. I always remember my paper that I was ready to now. You know how much therapy I went through to deal with the fact that I'd spent 6 months. So if any graduate students here, 6 months of nothing but to see the paper published, I just went home. I just said, that's it. Yeah, no, I agree with you. In fact, the West Coast North America story, other than some of these early geologists, Dickinson, for example, was somebody who wrote emails to say, yeah, this fits. The first evidence that sort of got the field thinking, well, maybe there's something to this dynamic topography of the West Coast, was studies of changes in drainage patterns, right? That was really, I wish I could remember the names of the people who did that. That was sort of subsequent studies that really showed a temporal consistency with the evolution of the dynamic topography there. So those are absolutely central. One of the great debates in South African literature is this uplift. When did it happen, right? Did it have, unfortunately, you don't have any uplifted beaches there, no Cretaceous uplifted terraces there. So questions on how quickly or how recent it uplifted hinge on how much erosion you think happened, how much precipitation was there. And so all of these things are brought to bear in these sorts of studies, but rivers has been a central part of at least the North American study. I'm less familiar with the Australian. In fact, I'm completely unfamiliar with it. There. Yeah, Anders.
I was wondering, with this dynamic topography, could you comment on that? That would be affecting anything in like the Red Sea sea level over longer, 500,000-year time scale?
Yeah, sure. So I was sitting in Peter's living room today when he came in, and I took the dynamic topography prediction that I've shown you, and I did what we haven't done, which is look at 125,000 years ago, and MIS 11, 400,000 years ago. And what I can tell you is surprising to me, I must say, but maybe not so when you see these rates, is your last interglacial elevations could be contaminated on order of a meter, right? So that's the differences we're talking about, right? People argue whether it's 7 or 8 or 9, and dynamic topography could give you a meter. And that's, that's a problem, right? Because dynamic topography, the models I've shown you, although I've tried to suggest that they're sophisticated, they're really in their infancy. I've said that already, compared to Ice Age models. The Ice Age predictions I've shown you have a 40-year history of being benchmarked. These things just last 4 years. So on one hand, it's a concern. On the other hand, we have to wait till they, I should also say that the 4 groups who do dynamic topography predictions never agree on amplitudes. So that's an indication of how early that field is. So I don't want to oversell it, but that's why I think you need to say more than it went up 20 meters. Are you explaining the proper location laterally of the shoreline? You have to say more than up or down now. And I think it's a relatively friendly group as far as it goes, and there'll be a lot of sort of community effort to fix that, although a colleague of mine suggests that community efforts in that case are the wrong way to go, right? Because you'll just start formalizing incorrect approaches, right? Any other? Yeah.
When you were mentioning in the very first part of your talk about modelers have to put ice in different places, hiding the ice.
Yeah.
Right, because they can't figure out where it is. But it made me think, does it have to all be ice? Does it have to all be glacial ice? Could it be ground ice? Could it be groundwater?
Right.
Are there other sources that would give a similar signal? Both the ground ice and the groundwater would have a much higher amount in a cold period than in a warm period.
Yeah, well, groundwater, so the people have looked at these very questions. What's the water inventory? How could it change? Even groundwater over a glacial cycle. And those are interesting questions, but the answers are never more than order a meter, right? And so there is an inventory of groundwater, but it's not going to explain the 30-meter difference, right? And this is where interdisciplinary work has to. Peter, we were at a conference a few years ago when the first ICE 5G came up, and you talked about this massive dome that had no glaciological realism to it. It could not have existed there. And so it existed only because those groups don't talk to each other, right? I mean, it was apparent even from basic glaciology that some of the large domes where people were hiding the ice just wasn't done in a realistic way on the basis of glacier physics. Right? I've tired everyone out.
Thanks again, Jerry.